So, in the previous lecture we have seen that ATM has mainly 4 types of traffic types. One is the constant bitrate, which is primarily used for doing circuit emulations for the transport of telephone, voice, etc. Then we have the variable bitrate, and variable bitrate also can be of 2 types, real time variable bitrate or non real time variable bitrate. And essentially the variable bitrate is the traffic which is coming from a VBR encoded video encoder or a voice encoder, or for that matter any real time encoders. Now it is for the variable bitrate VBR kind of traffic, the ATM offers statistical multiplexing gain along with the quality of service guarantees. The third type of the bitrate, the traffic types is available bitrate or the ABR traffic types, which essentially for the transport of the data packets. However, the difference between the ABR and the UBR is that the ABR traffic types also have certain guaranteed minimum cell rate. On the other hand, for the UBR traffic types, there is no quality of service guarantees absolutely at all. Now, primarily we have seen that CBR, VBR and ABR traffic types require certain quality of service guarantees. The CBR and ABR traffics, CBR and VBR traffics are subjected to certain admission control and signaling mechanisms. Okay. On the other hand, the ABR traffic is subject to certain flow regulations based on feedback about the congestion conditions in the networks. Okay. Now, we will now in the remaining lectures we will now focus how we can offer quality of service guarantees, okay, to a CBR or a VBR kind of a traffic in a statistical multiplexer like in ATM networks. Okay. In the first lecture we had seen that such quality of service guarantees can be given in terms of packet loss rate if each source specifies its probability density functions. Okay. Then what we do, we determine the density function of the combined output rate, and from that we determine whether the combined output rate exceeds the capacity or the bit or the maximum bit rate of the link. If it exceeds the maximum bit rate with a certain probability which is tolerable, then the calls can be admitted, otherwise the calls will be accordingly blocked. Now, since it is not possible for a traffic to characterize its probability density function, the ATM standardizing body like ATM Forum or ITUT has specified that the traffic must specify its characteristics in terms of its traffic descriptors. Okay. So, what are those traffic descriptors? Okay. So, we will just have a look at them. What are those traffic descriptors? So, the traffic descriptors which has been specified by the ATM standards are A, peak cell rate, which is called as PCR. 2 is sustained cell rate. 3 is cell delay variation, or what is called as CDVT. Now, the cell delay variations is a measure of the departure from the periodicity of the traffic. Then we have the measure of the burst tolerance, BT, and fifth is the minimum cell rate, or what is called as MCR. Now, the sustained cell rate is actually a measure of the average rate, okay, which the traffic will have, and on the other hand the cell delay variation, okay, is the departure from the periodicity of the traffic, maybe the departure from the constant bitrate traffic or the peak cell rate. The burst tolerance is a measure of the maximum back-to-back packets that can be sent, especially for the bursty kind of a VBR traffic, and the minimum cell rate is the minimum data rate that is required to be guaranteed, okay, to an ABR traffic. So typically a CBR traffic may be characterized by the peak cell rate and its departure from this periodicity, which is CDVT, cell delay variations, and a VBR bursty traffic can be characterized by the 4 parameters, that is the peak cell rate PCR, sustained cell rate SCR, cell delay variations and the burst tolerance, and on the other hand the ABR traffic can be characterized by the minimum cell rate. Now other problem is that when a source specifies its traffic characteristics in terms of these traffic descriptors and also specifies the quality of service attributes that the source wants, okay, then how will a network determine whether the call can be accepted or not, okay. That means how will a network determine that whether the traffic is admissible or not? For that the network requires 2 components, okay. What are those 2 components? The 2 components are that a network must first determine whether the traffic source is conforming to its advertised traffic descriptors or not, that is, it is conforming to its advertised traffic characteristics or not. And 2, the network needs an admission control algorithms, okay, which can determine whether the call can be accepted or not. Now a very naive admission control algorithms can be based on the worst case behavior, that is the peak cell rate, but that is not what we want. What we really want is some kind of a statistical multiplexing gain also should be there in the switch, okay. Otherwise, you know, there is no point in using an ATM network. We will simply degenerate to a circuit switch networks where the calls can be admitted based on peak rates, but of course at the expense of the inefficiency in the slot utilizations for the bursty VBR traffic. So let us see how a source can ensure that it is conforming to these traffic descriptors, and at the same time the network can monitor whether the source is indeed conforming to those traffic descriptors or not. In other words, we would like to see how indeed a traffic can specify its traffic characteristics in terms of these traffic descriptors. Now the ATM standards has specified an algorithm called generalized cell rate algorithm, okay, GCRA, which can specify all the these 4 traffic descriptors like the peak cell rate, the sustained cell rate, the cell delay variations and the burst tolerance. So let us see, you know, how we can specify these traffic descriptors. Now the ATM forum has standardized an algorithm called generalized cell rate algorithm called GCRA. Typically it is called as specified by GCRA T tau. The idea being that if a cell or a traffic source conforms to the nominal rate, of 1 by t, then tau is a measure of the tolerance, okay. So the source conforms to a nominal rate of 1 by t subject to tau tolerance limit. Now how does it happen? Let me just explain that, okay. Whether the source is conforming to an GCRA T tau parameters or not. Now one thing I would like to say is that this is a method of specifying the traffic characteristics through the deterministic bounds. Okay, so basically we are specifying some kind of a deterministic envelope on an otherwise statistical bursty VBR traffic. Okay, so let us see how we can specify that. Now let AK be the time at which cell K is observed. Okay. And CK is what is called as theoretical arrival time of cell K. Now theoretical arrival time is the time at which cell should arrive theoretically, okay, and AK is the time at which the cell K has been observed or it has has come. Then let us say YK is CK minus AK. Then we say that cell K is conforming to this GCRA T tau if YK is less than tau. That means the difference between the time at which the cell has actually come minus its theoretical arrival time, that should be less than tau. Okay, then the cell is conformant. It is non-conformant, it should YK is less than or equal to tau, and it is non-conformant if YK is greater than tau. Now if the cell is conformant, then we set CK plus 1, that is the theoretical arrival time of the K plus 1th cell, will remain CK if the cell was non-conformant, that is YK is greater than 2, or else it will be set as maximum of AK CK plus T if YK is less than or equal to tau. That means if the cell is conformant, okay, then it will be set to maximum of AK CK plus tau. Now essentially what we are trying to say is that tau is measuring the departure from the nominal rate, which is 1 by T. Okay. Now if you see here, then what is really important here for the cell to be conformant, that the difference between its theoretical arrival time and the actual time at which it has arrived must be within tau limits. Okay, otherwise the cell will be non-conformant. Okay, if it is greater than tau. Okay, and the late arrivals of the cells, okay, the late arrivals of the cell will actually delay, okay, the possible allowable theoretical arrival times, okay, of the K plus 1th cell, that we can see from these equations. Now let us consider an example to explain this point. Now what we are trying to really see is that, remember that a VBR traffic is generating a bursty variable bitrate characteristics. Now what we are trying to say, whether the arrival times of these traffics which are getting generated, whether the arrival times of the traffics which are getting generated, whether they are conforming to these GCRA T tau parameters or not, that is what we are trying to say. Now let us, for an example, consider that we have GCRA 10.3 as a parameter. Let us see that how an example works like GCRA 10.3, right. Now what is the matter of GCRA 10.3? Here T is 10 and tau is 3. Now let us say that C0 is 0 And consider an example where the arrival times are 1, 8, 19, 27 and so on. Okay. Now let us try to see whether these arrival times, as per the arrival times, they are conformant to these 10, 3 or not. Okay. Now the interpretation of this is that the nominal arrival rate is 1 by 10. Okay, that is what the interpretation of this is, with a periodicity or with a departure or with a tolerance of 3. That means the cells are expected to arrive, okay, at 0, 10 and so on, but there could be a departure subject to the tolerance of 3. Okay. Now let us see whether these cell 1, 8, 19, 27, whether it is conformant or not. Alright. So what is Y0? Now Y0 happens to be 0 minus 1, okay, that is C0 minus A0. Now remember that these are A0, A1, A2, A3. So this is minus 1. What is minus 1? Minus 1 is less than 3. So definitely cell 1 is conformant. Now since it is conformant, what will be the expected theoretical arrival time of the next cell? The expected theoretical arrival time of the next cell C1 will be set as max of 1, 0 plus 10, as per our earlier formula. That is what we are saying is max of AK Ck plus T. So that is what we are doing here, that is C1 is max of 1, 0 plus 10, and which gives us 11. So since the cell has arrived at 1, the expected theoretical arrival time of the next cell is required to be 11. But the next cell actually arrives at 8, okay, it arrives earlier. So let us try to see whether it is conforming to the GCRA 10.3 or not. So what is Y1? Y1 becomes 11, okay, minus 8, which is equal to 3, and since 3 is less than or equal to 3, 8 is conformant. Since 8 is conformant, we need to set the next arrival time, which is C2, and my C2 will be set as max of 11 and 8 plus 10, which will be set as 21. Okay. Now what about Y2? Now Y2 has come at 19. All right. So C2 was 21. 21 minus 19 is 2, and 2 happens to be less than 3. So indeed this cell is conformant. So the cell 19 is conformant, and since the cell 19 is conformant, my C3 is set as max of 21 into 19 plus 10, which is 31. Right. Now this is 31. Okay. Now the next cell, that is A3, comes at 27. Okay. It is expected to come at 31, but it comes at 27. Okay. So let us see whether the cell which is coming at 27 is conformant or not. Okay. Now if you see here, the expected theoretical arrival time is 31, and we will try to see whether the next cell is conforming to that or not. Now next cell is coming at 27. Okay. So our Y3 is 27, sorry, this should be 31 minus 27, which is 4, Now this 4 is definitely greater than 3, and therefore 27 is non-conformant. What has happened? The specification says, the GCRA 10.3 specifications, that since the previous cell had come at 19, right, the next cell, okay, can actually, come at 31 only, okay. Now since the next cell is coming earlier, 27, okay, if it had come at 28, let us say if it had come at 28, then the difference would have been 3 and the cell would have been conformant. But since it came a little earlier, okay, it is a violation of the departure from the periodicity, and therefore this cell will not be allowed. So it is indeed a non-conformant cell. Okay. Now another way of representing this GCRA 10.3 is by what is called as a leaky bucket algorithm. Popularly, this GCRA 10.3 has been implemented as a leaky bucket algorithms. I'll just explain through the same example how the things can be interpreted in terms of the leaky bucket algorithms. But before that, I just want to tell you that in practice, actually what will happen is that a traffic source is generating a variable bitrate bursty data. Okay. Now suppose it has negotiated with the network that it will specify its traffic descriptors in terms of a certain t and tau parameters. Okay. Now the network knows that the source will be transmitting its data in such a manner that it conforms to these t and tau parameters, but the source of course is generating a variable bitrate or bursty data which is essentially statistical in nature. Then what do you do at the source? At the source we will put this GCRA 10.3 traffic shaper at the source, whose output will conform to these GCRA t tau parameters. At the network it will put a similar GCRA t tau traffic regulator or traffic monitor, which will see whether the cells which are coming from the traffic source is conforming to those t tau parameters or not. Okay. So the device which will be put at the source will actually be regulating or shaping the output in such a manner that the traffic conforms to these t tau parameters, and at the network the device will be put to make sure that the traffic source is indeed conforming to those advertised traffic descriptors of t and tau or not. Okay. So now let us see its interpretation in terms of a leaky bucket. Now leaky bucket interpretation is something like this. Now this is a leaky bucket for GCRA t tau. Now this bucket has a maximum depth of t plus tau. Fluid, as I say, accumulates. Fluid accumulates in the bucket at unit rate. Okay. Now the cells are coming. Whenever a cell comes, it takes away t units of fluids. Okay. So each cell takes away t units of fluid. Now if a cell comes and it finds that the fluid contains in the bucket is less than t, so if bucket content is less than t, then the cell becomes non-conformant. Now, if we are putting this device at the source, then what we will do is that if a cell comes and if it finds that in the bucket there is less than t units of fluid, then the cell will be simply waiting in the buffer, and it will be transmitted only if the content becomes capital, content becomes at least equal to t here in the bucket. But if this device is put at the network side, and if a cell comes and if it finds that the bucket is not having enough fluids, then obviously that cell is not conforming to GCRA T tau, and then the network may drop this cell because this cell is not conforming to the advertised traffic contract. Now, if bucket content is greater than equal to cell, greater than or equal to T, then of course the cell is allowed to pass through, and the content of the bucket decrements by T. Now, let us take the same example that we had considered. Okay. Now, for this examples which we took was GCRA 10.3, this was the examples that we had considered, and the same example we will try to explain by the leaky bucket. Okay. Now, by this example, what does it mean? That initially the bucket contained where t plus tau, which in this case was 10 plus 3, which is equal to 13. So, we are trying to explain this for GCRA 10.3. Okay. So, here is a leaky bucket structure. Now, these cells are coming at different times, and we had assumed that the cells are coming at a time of 1, 8, 19, 27. Now, let us say f t minus denote the content of the bucket or amount of the bucket just before time t, and f t plus denote the content of bucket just after t, right. Now, let us see what happens. Okay. The first cell comes, that time the contents are 10 plus 3, 13. So, that means f1 minus this content is 13. Now, this cell comes 1, it takes away t units of fluids as we have said. So, when this cell goes f1 plus, the content becomes how much? 1, because it takes away 10 units of fluids. Now, let us say f8 minus, at f8 minus, sorry, the contents here becomes 3. Right. So, there are 13, you take away 10 units of fluids and the contents here becomes actually 3, not 1. Now, f8 minus, okay, already 3 units of fluids were there, and in these 8, okay, from 1 to 8, okay, total 7 units of fluids will accumulate. We are assuming that a fluid is accumulating at a unit rate. Okay. 3 was already here, so f8 minus is 10, okay, and f8 plus, that is, let us say this is the cell which has come at 1 and this is the cell which has come at 8. So, at f8 plus the content will become 0 because it will get decremented by 10. Okay. So, there will not be any fluid remaining now f8 plus. Now, the third cell which is coming at 19. So, f8 19 minus, alright, the content in the bucket would be how much? Here there were 0 and 8 plus to 19, we would have accumulated the content to be 11, okay, and therefore on F19 minus 19 plus, the content would become 1, okay. So therefore this cell will be conformant, this cell will be conformant, and this cell will be conformant. Now the fourth cell comes, which is at 27, okay. So now let us see what will be this content F27 minus. Now the contents at F27 minus would be actually 8, and this is not sufficient, okay, for this cell to pass through, because minimum 10 units of fluids are required in the bucket. So as a result, this cell is declared non-conformant. Now it has to, if this device, if we are using it at the source, then this cell 27 has to really wait in the buffer, okay, and how much time it has to wait? It has to wait for 2 more units of fluids to get accumulated. That means, you know, it has to wait till the time becomes 29, okay, till the time becomes 29, and the time becomes 29 minus, okay, then the content in the buckets would become 10, and then the cell can be passed through, okay. So now we have seen therefore how this can be implemented in terms of a leaky bucket algorithms, okay. Although we are, for the explanation purposes, we are saying here that the fluid accumulates in the buckets at a unit rate, and a cell takes away capital T units of fluids whenever it comes, but as you know, in practice it will be implemented simply as a counter. So what we are saying, that a counter has certain maximum unit up to which it can count, and in this case it is T plus tau. So the counter is incrementing at a unit rate, it keeps on counting, it is incremented at a unit rate, and whenever a cell comes, okay, the counter needs to be decremented by capital T. And if you find that by decrementing by capital T, the counter is not becoming negative, that means you can decrement it by the full capital T amount without becoming less than 0, then that cell is conformant and it is allowed to pass through, and the counter is decremented by the capital T amount, okay. So it can be, you know, this can be simply implemented as a counter. Now remember, again, at the traffic source, this works like as a traffic regulator or a traffic shaper, and at the network side it works like as some kind of a traffic monitor, okay. Now as we have seen that the traffic descriptors which a network is actually asking the source to specify are something like peak cell rate and the cell delay variation tolerance, okay. So now let us see, you know, how these conforms to those kind of a traffic descriptors. So let me just explain that. Now let us say that it is a CBR traffic source, okay. By a CBR traffic source, we mean it is a constant bitrate traffic source. Now this constant bitrate traffic source will be specified by what we call as the peak cell rate and the cell delay variation tolerance. Now typically in a constant bitrate traffic, it is assumed that the bits are coming at a constant rate, okay, but still there for the cell rate may not be constant, because there may be a deviation from the constant cell rate in terms of the packetization times and so on, okay. So even though the bits are coming at a constant bitrate, but the cells may not be coming at a constant cell rate. there may be a departure from the exact periodicity of this constant cell rate, and that is given by this cell delay variation tolerance. So we say that a CBR traffic, when it specifies its peak cell rate and cell delay variation tolerance, it means that all the cells should be conformant for GCRA R by PCR CDVT, where R is the line rate. Where R is the line rate. Now what does it mean? It actually means that the cell can come at the peak cell rate, but the CDVT, that is the cell delay variation tolerance, actually measures the departure from its exact periodicity. So now let us say, for an example, that if I say that GCRA 50, what is 50? 50 means that R by PCR, this is 5, and CDVT is 0. Now by saying R by PCR is 5, it actually means that the peak cell rate is 20% of the line rate. Peak cell rate is 20% of the line rate. What we are saying, that for the CBR traffic, it is expected that the cell should come at this constant rate PCR, but the cell delay variation will measure the departure from the periodicity. Now in this case, the cell delay variation, the tolerance, we are saying that it is 0. Now when we say that the tolerance is 0, then obviously the question is that in that case, what is the fastest cell sequence that is expected, and the fastest cell sequence that is expected will be -1. Now remember that you could come at 0, but since you have a cell delay variation tolerance of 0, you are allowed to come at -1 time as well. So fastest cell sequence is -1, 4, 9, 14, 19 and so on. Another cell sequence which will be possible is 0, 5, 10, 15, 20 and so on. Now this conforms to the constant bit rate of 50. If we had a tolerance, a cell delay variation tolerance, some tolerance, then it would have determined the departure from the exact periodicity, as we had considered in the previous example of GCRA 10.3. Now GCRA 10.3 means 10 is actually equal to the ratio of R by PCR. In that case, we are saying that the peak cell rate is 10% of the line rate. The peak cell rate is a 10% of the line rate, but so the capital T is 10, but the tolerance 3 is measuring the departure from the periodicity of this constant bit rate source. Now let us see how we can represent the burst tolerance. This is okay for the constant bitrate traffic, but what about the bursty variable bitrate traffic? Because the bursty variable bitrate traffic will actually be also sending back-to-back cells in the form of a burst. And again, for a long interval of time, it may not send any burst or any packets, and suddenly it may send a burst. So how do you represent such a variable bitrate bursty traffic? Through some kind of a similar mechanism like leaky bucket or so. Now let me just explain that through an example. Let us say a GCRA, let us say that GCRA, this time instead of 10, 3, let us take an example of GCRA 20 and 57. Okay. So, GCRA 2057. Now, let us say we have a traffic source. Okay, so let me just explain with this 2057, and then let us say that the cells are coming like at 0, 1, 2, 3, 4, so on. These are the cells which are sort of coming. Okay. Now let us see what happens. Now the leaky bucket will have 77 units of fluids initially, which is 20 plus 57, right. So these are the cells which are coming. So F0 minus, and the cell is coming at 0, the fluid amount was 77. Now when this cell came, the first cell at 0, it takes away 20 units of fluids, the capital T. So this is capital T and this is tau. Okay. It takes away 20 units of fluids. When it takes away 20 units of fluid, F0 plus, that becomes 57. Now the second cell comes at time 1. Let us see what is there, F1 minus. What is there in F1 minus? F0 plus, already 57 units of fluids are there, and 1 unit of fluid would have entered in the time, from 0 to 1, and therefore the total units of fluids that will be there will be 58. Now this cell will take away 20 units of fluids, and therefore the fluid content F1 plus will become 38. F2 minus. F2 minus is again 39, and F2 plus. Okay, F2 minus, remember here there is a 38 units of fluids, and one more unit of fluid will accumulate, and when the cell 2 comes here, it will decrement by 20, and therefore F2 plus will become 19. Now the third cell comes at F3, so what will be at F3 minus, just before the time 3, 19 units of fluids are already there at 2, one more unit of fluid accumulates and it becomes 20. So therefore when the third cell comes, it decrements by 20 and F3 plus becomes 0. Now these 4 cells 0, 1, 2, 3 are allowed to transmit. Now the fourth cell, if it comes, it cannot transmit here because it wants enough amount of fluids to get accumulated. So for how much time it has to wait? It has to wait till 20 units of fluids get accumulated. Okay, and 20 units of fluids will get accumulated only at the time of, since the fluid is accumulating at a unit rate, so the fluid is accumulating at a unit rate, it will have to wait till F23 minus, that is the cell will have to wait for 19 more units because it has come at time unit 4, it has to wait for 19 more units in the buffer before it can be allowed to transmit. Okay. Now what is the interpretation of this? Okay. The interpretation of this is that on an average, okay, the source can transmit, okay, 4 cells, okay, back to back, okay, that is what we have allowed. Now if the source again wants to transmit back to back cells, then it has to wait for how long? It has to wait till time 80. At time 80, see, remember, if these 4, 5 these cells are not transmitted, okay, you want to transmit again these back to back cell, let us say 4, 5, 6, 7, these 4 cells also have come. Now if you want to transmit 4, well, there will be enough fluid content at F23 minus, okay, and you can transmit 4. But then immediately if you transmit F23 plus will become, you know, 0, and therefore the 5th cell you actually cannot transmit. So if you want to transmit these 4 back to back cells, then you need to wait till the time 80, okay, at 80 time units, okay, at 80, 81, 82, 83 you can transmit 4 back to back cells again, okay. So what is happening essentially is that the source, okay, is able to transmit approximately 4 cells in a time unit of 80. If it has to transmit always in the bursty form, then it can transmit 4 cells in a time units of 80. This gives an average rate of 4 by 80, that is 1 cell in approximately every 20 time units. On the other hand, the burst it can transmit, a maximum burst is of 4 cells back to back, okay. So this actually represents a variable bitrate bursty source, a source whose average rate is 1 cell in every 20 time units, that is what its average rate is. On an average it can transmit 1 cell in 20 time units, and it can transmit a maximum burst of 4 cells back to back, okay. So this is like saying that the sustained cell rate, you know, the sustained cell rate or the average cell rate is 1 cell in every 20 time units, and its maximum burst size is 4 cells back to back, okay. So for the VBR traffic, therefore the ATM forum, you know, specifies that for VBR traffic the ATM forum specifies that the source should be conforming to the peak cell rate, the cell delay variation tolerance, and burst tolerance, and sustained cell rate. Now we just saw an example where we are saying GCRA 2057, which we were saying is a representative of sustained cell rate is 1 cell in every 20 time units, okay, and maximum burst size of 4 cells back to back. We saw that those 4 cells back to back, when they were sent as 0, 1, 2, 3. Later on they may be sent as 80, 81, 82, 83. So what is the minimum time interval between the cell, if you say, if you want to know what is the peak cell rate? What is the peak cell rate? Obviously the peak cell rate, the minimum time interval, okay, comes out to be as 1, and the cell delay variation tolerance comes out to be 0. So we say that this source is conforming to GCRA 10 and GCRA 2057. That is what this source is confirming. Okay. The meaning of these parameters is that a VBR source should be conforming to some GCRA R by PCR CDVT, cell delay variation tolerance, and GCRA R by SCR burst tolerance plus CDVT. What does it mean? If a traffic stream is coming, it should first pass through a leaky bucket, which will make it conforming to this GCRA R by PCR and cell delay variation tolerance, and then it should also conform to R by CR burst tolerance plus cell delay variation tolerance. This, okay, it should be conformant for both. This will give you that it is conformant to the minimum transmission time or the minimum interval between the cells, and the other leaky bucket, that is R by SCR and CDVT, will give you that it conforms to the burst tolerance and the sustained cell rate.